Sorting is a core concept in computer science used to organize data efficiently. Today we will explore insertion sort, a simple and yet effective sorting algorithm. Sorting helps in organizing data, making it easier to retrieve and analyze. From arranging books to managing database, sorting is everywhere. There are various sorting algorithms, each with unique approaches. Popular ones include bubble sort, merge sort, quick sort, and insertion sort. Our focus is on insertion sort, an algorithm that builds the final sorted array one element at a time, similar to sorting cards in your hand. What is insertion sort? Insertion sort is an efficient algorithm for small datasets. It inserts each element into its correct position within the sorted position of the array. Imagine sorting playing cards. You pick up each card and place it in the correct position among the cards already in your hand. That's insertion sort. Let's see the pseudocode. And as you see in the screen, this is the pseudocode for the insertion sort. Let's start with an unsorted array that contains the elements 5, 2, 4, 6, 1. We will sort this step by step using insertion sort. Start with the first element. The first element 5 is considered sorted. Move to the next element 2 and compare it with 5. Pseudocode. The start process begins with the pseudocode for I is equal to 1 to n minus 1. This loop goes on through each element from the second to the last. Compare and shift. Since 2 is less than 5, shift 5 to the right to make room for 2. Now 2 is placed at the start of the array. Insert element pseudocode to insert the element is while j greater than or less than equal to 0 and array of j. After inserting 2, the array looks like 2, 5, 4, 6, 1. The first two elements are now sorted. Move to the next element. Next, move to 4. Compare it with the sorted position 2. Since 4 is less than 5, shift 5 to the right and shift 4 to the left. Now insert 4 between 2 and 5. The array is updated to 2, 4, 5, 6, 1. The first 3 elements are sorted. This is the pseudocode for next iteration. Continue to the next element. Now look at 6. Compare it with the sorted position 6. Since 6 is larger than all, no shifting is needed. No shifting needed. 6 remains in its place. The array is now 2, 4, 5, 6. The first 4 elements are sorted. When no elements need shifting, the loop exists and the element remains in its current position. The last element. Finally consider the last element 1. Compare it with the sorted position. Since 1 is the smallest, shift all elements to the right and shift 1 to the left. Insert 1 at the start. Insert 1 at the beginning of the array. Now the array is fully sorted. 1, 2, 4, 5, 6. Pseudocode for the final insertion. Full sorted array. The array is now completely sorted. Every element is in its correct position. Time complexity overview. Let's discuss the time complexity of insertion sort. It varies based on the best case scenario. In the last best case, in the array is already sorted, insertion sort to O(n) time complexity. Best case, in the array is already sorted for I is equal to 1 to no shifting, only n comparisons continue. In the worst case scenario, when the array is in reverse order, every element requires shifting, leading to quadratic time complexity of O big O n square. Pseudocode for the worst case. The average case insertion sort also operates with big O of n square time complexity, similar to worst case due to the frequent shifting of elements. The pseudocode remains the same, leading to a big O of n square. Insertion sort has a space complexity of big O of 1. It sorts the array in the place, requiring no additional memory. Insertion sort is stable, meaning it maintains the relative order of elements. Insertion sort is simple, efficient for small datasets, and maintains stability. It works best on nearly sorted data. Let's solve an example using insertion sort. This example runs for big O of n square times as each element requires shifting as they are arranged in reverse order. The sorted array will be 2, 3, 5, 7, 9. Another example. By comparing and shifting, the final sorted array will be 1, 3, 4, 6, 8. Be careful not to skip elements or insert them incorrectly. Double check each elements. To avoid common mistakes, remember to compare elements properly and insert them in the right spot. Practice helps in mastering the process. Insertion sort is a fundamental algorithm that's easy to understand and implement. It's an excellent choice for small or nearly sorted datasets.